Hey everyone, this is Scott up at NCAR on the Vapor team, and this is a short tutorial on Vapor's transfer function. Again, Vapor is comprised of approximately 10 renderers, and each one of them makes use of a transfer function which applies color and opacity to your data in more or less the same way. And so I'll be going over some of the features very quickly in our transfer function. But before I move on, I have to make a quick announcement that on March 17th, coming up in a little bit over 2 weeks, there will be a free Vapor tutorial that I'll put a registration link to at the bottom of this video. So if this video does not cover all the questions that you have, please join us for this free tutorial and we can take questions and do it live. But if you can't make it, we'll probably do some more of those in the future, or you can leave a comment or a question at the bottom of this video, or lastly, you can email me personally at pierce@ucar.edu or my whole team at vapor.ucar.edu. And yeah, that said, hopefully we'll see you on March 17th. But the big question right now is, what is a transfer function and why is it important? Well, transfer functions are basically just filters. The term transfer function comes from circuits in electrical engineering, where we have an input signal that gets transformed into an output signal. It's basically just a filter, and they exist everywhere. We use these filters and transfer functions in our power supplies to power our computers. Usually we get 12 volts of DC power going into our laptop, and that gets downstepped into 3 volts, 5 volts, 9 volts, etc. to power the individual components inside of our machines. In fact, every single pixel that we look at on our computer screens has a transfer function applied to it because we need to filter those electrical signals. If we didn't filter anything, we would just be looking at noise all the time. And I would even maybe go so far as to say that everything in the universe is some kind of filter or transfer function. This is why the sky is blue, the incoming sunlight gets filtered, making it blue, and this is also why we can measure things like humidity from the refraction of GPS signals from GPS satellites. In visualization, transfer functions are a way of filtering out the massive amount of 3D data, usually 3D data, in our simulation data sets. On the left, we can see examples of transfer functions from other applications like Visit. Gosh, I think that's Photoshop, and we also have ParaView at the bottom. And basically, what these are showing is these are histograms of the data being sampled right now. So in the case of Visit and ParaView, they're looking at simulation data over here on the left. But on the top right over here, this is Photoshop, where you have transfer functions that show histograms of your red, green, and blue pixels that you snapped with your camera. Vapor's transfer function is over here on the right, and just like the other transfer functions, there is a histogram being depicted, and I believe we're looking at the pressure variable in a WRF simulation right now. We have a nice modal distribution, 2 tails and 1 big peak, and one thing that's very common amongst 3D visualization apps like Vapor, Visit, and ParaView is that they will draw a histogram like this, and then they will draw voxels or pixels according to the color values right underneath the histogram. So right here at the peak of our modal distribution, we're kind of coloring things like by an off red, and over at the right tail it's a darker red, and then over at the other extreme on the very far left we have dark blue. Vapor's transfer function also shows you the data bounds on the left and right side with this black bar. So the data bounds of this variable go from roughly -8,000 to roughly 1,000. And with all that being said, I think it's best right now just to dive right into Vapor. So I will exit out of my presentation and click on my V. It looks like I already have a session previously, but I'll start over for anyone who might like to see how Vapor gets run from the beginning. So I clicked on my V, Vapor has spun up, but I have no data. So I have a clear window over here. The first thing I'll do is go to my File menu, click on Import, and click on WRF ARW. The example data set I'll be using is from a WRF simulation of Hurricane Katrina. And I'll pick any file, doesn't really matter which one. And so now I have my domain. I can spin it around, like maybe you've seen in our tutorials, but to demonstrate the transfer function, what I'll need to do is create a new renderer. And I think our volume renderer depicts our transfer function in probably the best way, in the simplest way too. So I'll click on our new button and select volume, click OK, and I've now instantiated my volume renderer. To turn it on, I will click on this enabled button. And here we have our big red brick from Katrina. I guess we have a blue little spot here at the bottom. But the reason we have this red brick is because we haven't filtered any of the data. We're looking at every single data value in the data set, and it's completely opaque, so we can't see what's going on inside the hurricane. We can see in my variables tab over here that we're looking at pressure, and that's just fine. We want to get to the transfer function, so all of the transfer functions for every renderer are kept in the appearance tab. So I'll click on appearance, and there it is, top and center. This thing is kind of the heart of Vapor. So I click on my appearance tab, my transfer function is at the top, and again, here's my modal distribution of pressure. The colors are being applied to the data values according to this color bar down here. And to apply opacity, that's the second step, which is also why 3D visualization is so challenging. You're not just applying color to a slab in a simulation. You're looking at an entire 3D volume, and you have to apply opacity to it, or reduce opacity to a lot of values in order to see the observables you're going after. So opacity is all controlled by this black bar up here, and there are control points. I can click on a control point, and I can see a data value. So at this control point, I'm looking at roughly negative 1700 pascals. At this one, the maximum roughly 1300, and you can see that these kind of associate with each other. The control points on the color bar and the opacity bar can all show you different heuristics in your data set within this sample. So with a modal distribution, what I usually like to do with my histograms in my transfer functions, when I have a modal distribution like this, I like to hone in on the meat of the data, where everything really is. And so in order to do that, I can drag these extents and narrow them in so that I'm seeing more of the witch hat, because there's a lot of data values on the left, there's a lot of data values on the right, but there are not as many as there are in the middle of this witch hat. So by dragging these two control points down here, I can hone in on the peak of my witch hat. But you can still see, I'm looking at a big brick. I can see a lot of the values on the outside of the volume, but there's still no transparency. I can't see through it. And so in order to apply transparency, what I'll usually do is mask out the values at the peak of the witch hat, so that the values on the tails are accentuated. So now we're looking at low values on the left side, which are about roughly negative 600 to, and on the right side we have positive 500. But all those values are being accentuated right now. I can kind of play with the opacity to increase and decrease the representation of those values. But right now I'm not looking for anything in particular. Let's just make something up, and I'll look at this tail out of the center of the hurricane. And by the way, all of the values that exist on the left and right sides of the histogram that are not being shown in the histogram, i.e., I guess in other words, all the values that would extend out to the right of the histogram, they are having opacity values and color values applied according to these 2 points. So everything greater than 509 in my current variable is going to be shown at maximum opacity, and it's going to be shown in a dark red. So that's how to control, I guess, the extents of the histogram, the color and the opacity, but there are a few more things worth showing. We have built-in color maps, so you're not stuck with the blue to white to red combination. of colors. We have a selection of diverging, highlighting, and sequential color maps. And there are use cases for each one of these. With a modal distribution, you're usually best off using a diverging color map where you go from one color at an extreme into a neutral color, usually white, into another color. And so this is a diverging color map where we are depicting the tails of the histogram with blue and red. But if you don't have a modal distribution, you're probably best off using a sequential color map. And so here are the color maps that we provide for that. And I don't know, just for kicks, I'll add thermal, and I don't know. Usually with a modal distribution, you want to show the two extremes of the histogram. So it usually makes most sense to use a diverging color map for that. Another thing I can do is take these color control points and move them around if there's special, I don't know, special editing for some reason that I want to do to show my observable. I can do that, but I can also save the transfer function through the Save Transfer Function button. Yeah, I might have gone too fast there, so I'll click on my toolbar, click Save Transfer Function, and I'll call this test worf. And now I think in my home directory I will have that transfer function saved. So if I go back over here and make some changes that I don't like later, I can go back and load my previous saved state transfer function from my home directory, testworf.tf3. And there we go. Everything is back and reverted. So those are the basics of the transfer function. If you have any questions, please reply to this video, and we're pretty on top of it. Or you can email us at vapor.ucar.edu or me personally at pierce@ucar.edu. I'll put links on where to download Vapor. And one last plug, we have a 1-hour free Vapor tutorial that's a live session coming up on March 17th. So I'll put a link to register for that if you're interested. So thanks for watching the video, and hopefully see you at the tutorial on the 17th.